Hello everyone. As far as I know, since the COVID-19 pandemic occurred, many patients needed a mechanical ventilator to help them breathe due to inspiration issues. Therefore, after a while, there was a leak of ventilators, so many of engineers, students, and talented guys participated to produce good devices that might be helpful. There are many of designs on the internet, but some of these designs don't occupy pressure sensor on the patient circuit to keep an eye on the lungs pressure and don't provide either PEEP feature or trigger feature. It's not that easy to build a ventilator since the respiratory system is very complicated. And as we already know, the lung pressure is very critical aspect during mechanical ventilation. Thus I am going to share my result with you about using small pressure sensor. In this video, we will see how to use a pressure sensor that uses Wheatstone bridge to measure the pressures, and we will see the calibration process to get a precise reading from the sensor depending on known pressure. The concept of this video is simple. Warning, this video is just for educational purposes, so if you want to use it, please use it on your own risk. The sensor that I am going to use has a small range of measuring from -5 to +5 psi, since the measured pressure range will be smaller than that, and it will do the job as we intended for either PEEP or trigger or any other goals. Also, we will test the circuit output using oscilloscope to make sure the output signal is readable by the microcontroller ADC correctly without much noise. In my case, I'm going with Arduino Mega that has 10-bit ADC resolution. What I've used to measure the pressure on the patient lungs, I've added a sensitive pressure sensor on the patient circuit, like this pressure sensor from Honeywell, 26PC05SMT. This sensor belongs to 26PC series, as you can see in the datasheet. Don't use these products as safety or emergency stop devices or in any other application where the failure of the product could result in personal injury. So please use it on your own risk. The general information about this sensor. The sensor is SMT, aka Surface Mount Technology. It uses piezoresistive bridge and Wheatstone bridge configuration. So when pressure is applied, the bridge resistance changes, and the sensor provides an output signal proportional to the input pressure. Therefore, a differential voltage proportional to the pressure difference between port 2 and port 1. Here I am going to use port 2 to measure the applied pressure, and port 1 as a reference pressure. The sensor can handle up to 16 volts, so I'm going to use 10 volts as a power supply. Here are the sensor pin out. Pin 1 is VCC, pin 3 is GND, pin 2 and pin 4 are the output pins. Pin 2 will be the positive output and pin 4 the negative one. Here is the sensor that I have, and as we can see, the output is amplified according to its datasheet. Port 2 will be to measure the applied pressure, and port 1 for the reference pressure as I said earlier. The sensor has a standard port configuration. Check the datasheet for more information. I will leave the links in the video description. After we know the sensors that we are going to use, let's move to the circuit schematic. Since the sensor uses Wheatstone bridge configuration, then the output is the difference between V2 and V1. But the difference is in millivolt, which can be difficult to measure using microcontroller ADC. And we have two voltages to measure to calculate the difference between the two. Therefore, we have to amplify the difference using an operational amplifier. As we saw, there are two voltages to deal with, so we have to use an op-amp in a differential mode, which will make it a subtractor, and the output will be high enough to be read by the ADC. This op-amp will amplify the input by 56 times, or the ratio R2R1. The output equation is this. Thus, the output voltage will be proportional to the difference voltage between V2 and V1, and that will make the measurement easy and correct. This is the full schematic of the sensor circuit. As we can see, it contains 5 parts: the pressure sensor, the filter to smooth the sensor output, the amplifier as I said earlier, the output to ADC pin of the microcontroller, and the power supply, which is in my case 10 volts. I have designed the circuit with the help of EZDA program. Here where the sensor will be connected, the two capacitors are to filter the sensor output, The amplifier circuit which I used is the LM393P op-amp. You can use any op-amp. Then here we have a capacitor to smooth the amplifier output signal, as we will see later on oscilloscope. I also made the PCB of the circuit. In case you want to print it, you will find the Gerber file with all the file as always in the video description. It looks like this. Now let's test the circuit using the oscilloscope to see whether the output is stable and high enough to be readable by Arduino or not. As we know, Arduino has 10-bit ADC resolution. Therefore, the minimum voltage that can be measured is 4.8, which is higher for the sensor output. Actually, 1 mV means something for us, considering 1 mV makes a huge difference in the sensor readings since its output in millivolts. As we can see on the multimeter, the sensor output voltage has been amplified and the voltage that we got will be the offset. In other words, it will be the 0 point that will be subtracted from the analog reading, as we will see on the code later on. On the oscilloscope, the output signal is smooth without much noise on 500 mV. Thanks for the capacitor. Let's decrease the channel voltage to lower voltage to see deeper how the signal become. Because we need the signal to be smooth even below 4.8 mV, so the ADC will have no problem with the noise that might occur and make sure doesn't pass 4.8 mV. As we notice that the capacitor in the output has smoothed the signal pretty well. On 2 mV range, without the capacitor, we clearly see that V peak to peak is a bit higher than 5 mV, which will affect on Arduino readings. Let's put the capacitor back and recheck the signal shape. Comparing V peak to last one is less than 1.2 mV, which will be suitable for Arduino ADC, and the output voltage is very stable. It's still there some bouncing in voltage about 0.1 mV, but it's fine. I'm going to apply a small positive pressure and negative pressure on the sensor using my breath pressure, since that will be its job. Anyway, the signal is still stable and the output is proportional to the pressure correctly with good sensitivity. By the way, the tube that I am using is a medical feeding tube, 5 French in diameter, means about 1.6 mm, which fits the sensor port. Moving on to the code. I'm using an I2C LCD to display the pressure values. If you want to use one, you should change the I2C address to match your LCD driver. First of all, we should measure the offset of the output as I mentioned earlier. The connections are pretty easy, just connect the output of the circuit to any analog pin of Arduino and make the G&D command between Arduino and the circuit. Select the board with the associated COM port and upload the code. Open the serial monitor to check the analog reading, that will be the offset, and make sure there is no pressure applied to the sensor. In my case, the offset is 17. Replace it with the pressure offset in the code and re-upload the code. The second thing to do is to calibrate the sensor output using either a known pressure or using a pressure meter with good accuracy. As you might notice at the beginning of the video, I used an old gas tank and I put it about 500 mAh of air in it to use it as a pressure source. As you can see, the measured voltage now is 0 volt, so we are safe to go. I'm going to apply 100 mm of mercury on the pressure sensor and the pressure meter simultaneously to get the measured voltage on the serial monitor to use it in a simple equation. Here I've got 0.48 mV in case of 100 mm of mercury. After that, we just need to divide the applied pressure on the measured voltage to get the calibration value. In my case, it's 208.33. Copy it in the code and re-upload it, and you are ready to go. The final result is impressive. The sensor is pretty accurate according to the pressure meter that I have, and the pressure is quite stable, with a small margin of error. Even it's accurate when small pressure is applied, that will be useful to measure the breeze pressure or any other small pressure. Both of the pressure sensor and the pressure meter is connected to the same pressure source. Now I think it's possible to give it a try and test it. We even used this sensor in the ventilator that we made recently for PEEP and trigger, and everything went well. So this is my result dealing with a small pressure sensor from Honeywell. I hope it might be helpful in some ways in your future application, or at least interesting. In the end, if you have any question, please leave a comment and I will try to answer it. As always, be the creator of your ideas. See you next time. Thanks for watching.